Welcome back to Zenith Poker. Today we'll be starting a new series called Poker Misconceptions. And in this first video, we'll be discussing why more bet sizes are better. All right, one of the most prevalent and quite false misconceptions in the poker space is this one. It goes something like this. If the expectation in the solver is the same for two strategies, then you should choose the simpler strategy. And this misconception has multiple parts associated with it. You can come to this idea if we sort of break down the logic behind it. So the logic behind this misconception is in three parts here. The first is that the solver EV of the strategy is a good approximation for the game EV. The second is that the EV of a strategy in one sim can be compared to another sim. And the final assumption is that simpler strategies are easier to learn and implement. And today I'm going to talk to you about why these three assumptions are wrong. I will show you some examples of how they're wrong, and then we'll talk about the best way to move forward. So let's talk through these assumptions one by one. So the first assumption here is that the solve EV of a strategy is a good approximation for the in-game EV. Now, this one is a big misunderstanding for a lot of people. And in order to really explain it, I need to discuss what the solver actually is doing and how poker players use the solver. So the solver is just a piece of software that's run on your computer or your server or basically any kind of hardware. What it does is it takes in an abstraction and then creates a strategy pair or a strategy set, depending on how many players you've got, for that abstraction known as the solution. And it does this using various mathematical techniques to come to a equilibrium solution for that particular abstraction. And the reason why we need to do this is because no limit hold'em as a game is incredibly large. And so it's impossible to actually solve no limit hold'em, heads up, multi-way, doesn't matter. The game is just too big. So instead what we do is we create a model of the game called an abstraction. And so an abstraction, most people would think of this as sort of the game tree, or a number of bet sizes at each node, and then all the possible betting and action sequences that take one node to another node in the tree. So with the game tree and the starting game state, we build an abstraction, and this abstraction is what the solver is actually performing its computations on. It's creating a strategy for the abstraction. Let's take a think about how poker players actually use solvers to generate good strategies. So the first step is we observe information about the game, and then we translate this information into something that the solver can use. So something that we can put into a computer, into the solver, into this piece of software that the solver can actually perform calculations on. All right. Then the next step is taking this information and creating a simulation configuration. So basically what we're doing is we're setting up a game tree. We're putting in information such as preflop ranges or player tendencies or different bet sizes that you would prefer to look at. And you put all this information into the solver software, and the software uses this information to create an abstraction. Either the software sends the abstraction to the hardware, which then gets solved in memory and computation. Then the solution gets output, right? The solution is a strategy, often it's a strategy pair for heads-up solves, but we can call it a strategy set for multi-way solves. It's just a bunch of strategies for each player on that particular abstraction. And the claim for a lot of solvers is that these solutions are close to the Nash equilibrium for that abstraction. So once we have the solution, the solver software displays that solution in a way that sort of we can understand, right? We would go through and traverse the tree, and we're essentially going to train ourselves using the information from the solution. And then finally, what we do with this information is we update our own strategy. So the solution is essentially just a list of numbers, values that give strategy information from the abstraction that we put in. We look at that information and we use that information to update our own strategy. And then we implement our strategy in the game itself. So notice for each of these 6 steps, we're not actually solving no limit hold'em. So the no limit hold'em is not solved at any stage. What we're doing is we're solving abstractions of the game. So these abstractions aren't the game. They're limited subsets of the game itself. Information from those abstractions is just 2 strategies playing against each other in the abstraction. They can't play outside the abstraction, right? Because it doesn't exist. The solver doesn't know about any bet sizes that you didn't put in. Any information that you didn't give it, it can't compute. So the expectation, right, the EVs that the solver generates are just averages based on the strategies inside the abstraction. They're not EVs for the actual game, right? They're just EVs for that particular abstraction of the game. In reality, we don't actually know the EV of our own strategy. And we can never really know the EV of our strategy because the EV of our strategy depends on the strategy of all of our opponents. If we know our opponent's strategy completely, and completely I mean every single hand played in every single possible way, in terms of every single bet size, how that hand plays against every possible bet size that our opponent will use in every possible situation. Once we know that information, right, which we can never know, then we can calculate, precisely what our expectation is for any particular strategy that we have. And we can actually calculate a strategy which maximizes our expectation against those opponents. So we don't actually know the EV of our strategy, right? The EVs don't mean anything. They only tell us what one strategy expects to win against another strategy within an abstraction which we've given the solver to calculate. So the next part of this misconception is that the EV of a strategy in one sim can be compared to another sim. So this misconception comes from the fact that we often use different abstractions for the same subgame, right? So if you have a postflop solver with just 2 players or 3 players or whatever, and you want to find information about the postflop play, generally what a lot of poker players will do is they'll take, preflop ranges, and you'll put that information into the solver. You'll generate a tree as the game tree, and the combination of the preflop ranges and the game tree and the rake becomes an abstraction for the solver, and the solver solves that. And so it's quite easy to think that if you have the same sort of starting state, it doesn't matter what tree that you put in, what game tree that you put in, and so that you can actually compare the EVs between them. Well, no, this is not the case, right? What the solver is actually doing is it's just solving that particular abstraction. It's not actually solving that subgame. So it's just creating strong strategies for that abstraction, and then it tells you what the expectation is for those strategies inside that abstraction. So you can't actually compare the strategies of the EVs of two different strategies, because the EV of one strategy in one sim has different bet sizes than the strategy in another sim, which can't be directly compared, right? It's just sort of undefined in both sims. You can't say the EV of one particular action is X, right? And you can't compare that to another sim if that sim doesn't have that same action in it, right? It's X here and it's undefined here. So when you have a sort of an average across different actions, which is what the expected value is, you get sort of a bunch of undefined values for the two different sims. All right, so here we've got example one. So example one, it comes from the small blind versus button three bet pots formations. We got ace, 8, 7 with a flush draw. So this sim looks something like this. We've got 6 different bet sizes on the flop with an all-in size down from 10% up to the pot size bet. Look at the tree size, 4 gigabytes, fairly large. Lots of sizes for both players throughout the tree. So in this example, we're going to compare similar trees and show an example of how you can use the EV number here in the solvers to make some comparisons. And I'll talk about why that's the case. Generally, it's not a good idea to compare the EVs between different trees. But if the tree is quite similar, then you can actually make valid comparisons. So let's have a look at this flop 10p. So we're looking at the difference between the different trees. So this tree is actually the exact same as the other tree, with the exception for the fact that the small blind is only allowed this 10p bet on the flop and the jam. So it's only allowed this 10p bet on the flop. So these two trees, the equilibrium tree with the 887, which we see, and the flop 10p, are similar with the exception that in this flop 10p, the small blind is limited to only make this 10p bet on the flop. Here we've got the flop 25p. It's the same idea. The small blind is limited to only bet the 25p. So it's the exact same as the other tree, except we've only got a single size being able to be used. So for that reason, you can actually make valid comparisons in the EVs, because the rest of the tree is the same. The strategy is somewhat valid in between the two. But you got to remember that the solver does what solver does, and it ends up producing a strategy for that particular abstraction. So here, for example, this flop 25p, the button's response to the flop 25p is actually going to be different than the button response in the large sim. So here, the large sim against the 25p, there is a subtle difference in between the two. So here, for example, 14.6% raise frequency in the large sim versus in this flop 25p, we only see a 9.48% raise frequency. So there are going to be subtle differences in the strategy. Okay, so with only using a single size, there is going to be an overall EV loss between the large sim. So the large sim with 1, 2, 3, 4, 5 bet sizes and the all-in is going to have an EV of 11.77 for the entire range, but these other sims with a single size can only have a maximal EV of 11.74. Why is that the case? It's because the opponent, the button, will have a slightly different strategy in response to each of these sizes than in the large sim, and that reduces the EV of the small blind. So if your opponent knows that you're playing a single size, they can actually produce a counter strategy which reduces your EV. But what you can do in response to that is calculate the counter strategy. So here I've got this in the flop crusher. I've essentially locked the button strategy to assume that the small blind is only playing a single size. So this flop 10p down to flop 100p, these 5 different simulations have been locked into this particular simulation here. So the responses to each of these is the same as in the respective size. So here there's 10p size, the button's flop strategy is locked. So given that information and the button strategy is locked to the same responses in those other sims, we get a different strategy from the small blind, which is the counter strategy, which looks something like this. It's got loads of different sizes, the jam size being taken, the pot size bet, the bet for quarter pot, 10% pot being taken. And we end up with a result that the small blind actually has an increase in the EV playing this flop crusher. And we can see there's an EV difference around 8 big blinds for 100 hands. So whenever there is a deviation from the equilibrium, there is a response that can decrease your opponent's EV. So here we've looked at the large sim, AS87. This one is as close as we can to equilibrium given the 40 gigabytes of RAM. The single size simulations here are a deviation from that. It's a deviation from the equilibrium. We're locking the small blind to only bet a single size. And as a result, the button will create a counter strategy which reduces the EV of the small blind. But if the small blind then actually calculates the counter strategy to the button's adjusted strategy, the small blind can now win some EV back against the button by reintroducing those additional sizes into the strategy. So this is an example one. This example one was an example of when you can use the EVs to make decent comparisons. You really can only do it in situations where the trees are very similar. So the same tree with the only bit difference being a single node. So here, for example, the multiple sizes down to one size and then back to multiple sizes again. And copying, pasting in strategies from one sim to another sim does give you valid EV comparisons. So in fact, we can see that the Ace87 large sim and the flop crusher sim, these two simulations are in fact the same game tree, the same abstraction, but there's two different strategies. So here in the Ace87, we've got a near equilibrium strategy for that abstraction, and here in this flop crusher, we've got a deviated strategy for both players. The small blind is calculating an exploitative strategy against the buttons strategy, which is exploiting one of these single size strategies. So you have a quite valid comparison between the EVs of this tree number 1 and tree number 7, Ace87 and flop crusher, because the trees are exactly the same. The only difference is the strategy. Okay, so here's the second example. So same formation, different board, Jack 7-3. Now we're going to look at a situation where the comparison of flop EVs is actually going to be invalid. So here we've got the Jack 7-3. This is a large sim. We look at the tree to see how big it is. So here 42 gigabytes, so fairly large, lots of bet sizes for both players across all 3 streets. So now let's look at a comparison where you've got an EV that's roughly the same, but it's an invalid comparison. So this would be this 50p only. So here there's 50p only. We've got the EV for the 50p only to be 12.43 for the small blind, and the EV of the large sim to be 12.42. So you can think that, okay, well, these two sims have roughly the same EV. There's only a 1 big blind difference. You'll think that maybe you could play according to this 50p only, because this tree is a lot smaller. It's only got the 50% bet sizes for both players. But this abstraction actually cannot be compared to the larger abstraction because the abstractions are just too different. And I'll show you the reasons why. So say, for example, we want to build up from this 50p only strategy and add additional sizes to one or other player. And we'll see what happens, and we'll get closer to the Jack 7-3 large simulation. So if we add bet sizes to just the flop, all right? So here I've got this OOP flop plus. This simulation here, it's the same as the other simulation, except it has the extra bet sizes on the flop. The button doesn't have any additional sizes. So here, the only difference between this simulation and the 50p only simulation is that the small blind's flop strategy is much more complicated. We can have a valid EV comparison between this 50p only and this flop OOP plus. So we've got an EV difference of 9 big blinds per 100 hands, so 12.52 versus 12.43. So suddenly, the small blind, just adding the flop sizes, gives a difference in expectation of 9 big blinds. That's not the only example we've got here. We've also got OOP turn plus, which is the same situation, except instead of the flop, I've only given the small blind the additional bet size on the turn. So the flop strategy actually looks fairly similar to the original 50p only, right? If you look at it, we've got 75.4% betting out of the small blind in this 50p only. And in the turn plus, we've got 72.7%. So sort of similar betting schema, except we've got the additional bet sizes on the turn. And with those additional bet sizes on the turn, you can't see as much of a difference, but you get this massive EV difference here between this 50p only and this OOP turn plus, right? Once again, you get a 9 big blind increase in the EV, so 9 big blinds per 100 hands. And then lastly, we've got this OOP river plus. The small blind has the additional bet sizes on the river. And with these additional bet sizes on the river, and only the river, you suddenly have an increase of EV of what looks like to be 14 big blinds. So with only a single street having additional sizes, you get big increases in expectation for one player or another. So here, these are the examples for the out of position player, similar examples for the in position player, IP flop plus, IP turn plus, and IP river plus. So here with this 50p only, you get a 1 big blind difference with adding additional sizes for the in position player, 1 big blind difference on the flop and the turn, and then a 6 big blind under hand difference for adding the additional sizes on the river. So here in this example, you get some subtle differences which improve the EV for the button player. And so these are somewhat valid comparisons, right? You can validly compare this 50p only to one of these other sims, because you only have some differences in the strategy for one player, right? You can make a somewhat valid comparison. It's not exactly valid because the two abstractions are not the same, but you can see that if you add additional sizes, you get an improvement in the expectation for one player or another. Okay, so let's take a look at what happens if it's across two streets. So let's look at this for 50p only. So tree number 4 with a 12.43, this OOP flop plus turn plus. So here, this flop plus turn plus, it's bet sizes on both the flop and the turn for the out of position player. So we get a strategy that looks like this. It's fairly aggressive, lots of different sizes, and checking, and plenty of going for the check raise, check min raise, being very aggressive. This flop plus turn plus, right? So the bet sizes on the flop and the turn give a big difference in EV to the out of position player. So we go from this 50p only up to this flop plus turn plus. Here we get an EV of 17 big blinds per 100 hands, which is huge, right? 17 big blinds per 100 hands. And this is against a solver, which is going to have the optimal response given its only 50% size for the in position player. All right, and now let's have a look at the turn plus river plus. So this is two streets together, so the single size for the flop, and now two streets of multi-size betting on the turn and the river. Flop strategy looks somewhat similar to the OOP only, but we get a massive difference in the turn and river strategies because the out of position player has all those additional bet sizes on the turn and the river, and we get a huge increase in the expectation from this 50p only to this out of position turn plus river plus. So with the two streets of additional betting, we get a EV change from 12.43 up to 12.67. So while these comparisons in EV can't really be compared because it's different abstractions, you can make some directional comparisons. So we're saying that the OOP only, if you add additional sizes on one street, sure, you can sort of compare it and you see an increase in the EV for one player. If you add it to a second street, once again, we're comparing this OOP flop plus to OOP flop plus turn plus, we get another increase in EV. So this comparison with this one is sort of what we're looking at, but it's directional. We're saying that by adding sizes to a single street, by adding also sizes to a single street, you get an increase in expectation. You can make that claim. The amount of increase in expectation is not something that you can really claim so easily because the two abstractions are actually different. So these OP flop plus turn plus and turn plus river plus are very different in their abstraction to this 50p only because of the additional sizes across multiple streets for the out of position player. So I can't actually compare the EVs directly, but I can definitely say that we have an increase between this, where we've only got one bet size, this 50p only, where we've only got one bet size, to this flop plus, or this turn plus, or this river plus, where we've got multiple sizes on a single street. So I can make that claim that I do get an increase in EV. And then I make another comparison here between this out of position flop plus, turn plus, the river plus, to the two streets of betting. So here, flop and turn, or turn and river. And I see that there's an additional increase in expectation by adding a additional second street of multiple sizes. So I can say that there's a increase in expectation by adding an additional street of multiple bet sizes. And the magnitude of that expectation increase is going to be significant. So that was two streets of betting, and now we've finally got this OOP max. Right, this OOP max, we look at it, very aggressive, right? Two main different sizes on the flop. What's going on is that we've got the out of position player having three streets of bet sizes, and suddenly there's going to be quite a big difference between the 50p, big difference in the strategy, and a big difference in the response. So the button is going to try to respond as best as possible. This button response against the 50p looks like this. This button response against the check looks like this. It's going to actually be somewhat similar. Same kinds of hands are going to be doing the same sorts of frequencies between the two different simulations against the 50p bet size and against the check. It's going to be somewhat similar, except because the out of position player in this OOP max has all three streets to change the bet sizes accordingly, the out of position player has a massive edge against the in position player. And you can say that there's going to be an increase in the expectation. The actual magnitude is not going to be something that you can actually really say because the two abstractions are very different and the strategies aren't actually locked. So you can compare this EV between this 50p only and this OOP max. You get a 31 big blind per 100 hand difference. But really, you can't really say that there's that magnitude of difference. You can say that there's a directional difference. So adding an additional street of sizes, here we've got this OOP where we add either one street, flop, turn, river, right? And then we have two streets, flop and turn, or turn and river, right? We get an increase there, right? So going from 12.52 to 12.57 with a single street, up to 12.6 to 12.67 for two streets, up to 12.74 for three streets. So there's always a directional increase in our expectation by adding an additional street of multiple bet sizes compared to single bet sizes on one of those streets. And this will even occur in preflop. In preflop, if you're on a preflop simulation where you've got multiple bet sizes for a single player on the preflop street, you also add expectation to the player with multiple bet sizes. And so each additional street where you've got multiple bet sizes will increase your expectation and even further increase your expectation against a player that only has single sizes. And the player that only has single sizes can't do anything within their own strategy to improve against you. The only thing that they can do is add additional bet sizes to their own strategy. The only way that this OOP max strategy for the small blind, where they've got multiple sizes for the flop, the turn, the river, the only way that the button can actually improve against this small blind strategy is to add more sizes to their strategy. And so you end up with this OOP max getting closer to the original thing that we looked at, this Jack 7-3, where both players have lots of sizes in their game tree. So both players have lots of sizes here. We see that this comparison between this OOP max and these flop, turn, river strategies, they're somewhat directionally, at least, valid to compare. You can't make the actual comparison because the abstractions are very different, unlike in the first example that we looked at. where the abstractions were the same, and you did have a valid comparison between the two strategies in the same abstraction. Here we're looking at different abstractions, so the magnitude of the expectation cannot be adequately compared, but directionally, if you add more bet sizes to one particular player or another, you get a directional increase in expectation for that particular player. And the other example here I've got is IP Max, where I've done sort of the same thing, except the in-position player has multiple sizes across all three streets. And we can see that the EV drops for the small blind. So if the small blind only plays the 50p, they're punished in terms of their expectation because they only play a single size versus the button that plays multiple sizes. So these two sims, this 50p only has an EV of 12.43 and this Jack 7-3 has an EV of 12.47. So initially we thought, okay, well, these two sims have almost the same EV. Maybe I can just play 50p only. The answer is no, because these two simulations, the 50p only and this large sim, are very different in their abstraction. And so you can't actually make a valid comparison between these two numbers. So these two numbers, 12.47, 12.43, are totally meaningless when compared to each other because the two abstractions are completely different. Only when we add additional sizes to one street for one player and then we build that up across multiple streets for both players, we go from the 50p only up to the large sim. We can see that if you add more bet sizes for one player on more streets, you get a improvement in the expectation for that particular player. And if you do it both ways, we end up close to this large sim, which is what we are looking at when we study sims that we try to run close to equilibrium. A final assumption in this misconception, and that is that simpler strategies are easier to learn and implement. What we're doing as poker players when we're studying with solvers is we're looking at the solution and we're studying it and we're using it to improve our own game. We look at different sort of themes and sort of techniques or bet sizing sort of schemes and different lines and how the two, really strong strategies that we've generated play against each other. When we're thinking about whether or not a simpler strategy is easier to implement than a more complicated strategy, that's not really the case. It's sort of true, but it's sort of not. It's not really relevant what strategy we're trying to play. What's most relevant is the strength of the strategy, right? So if we have two different strategies, one is simply stronger than the other. If we're trying to learn from the stronger strategy, we would expect that our own strategy, the strategy that we implement in game, not the one that we're learning from, the strategy that we implement in game ends up being stronger than if we learnt from the simpler strategy. If it's the case that, a really simple strategy is easy to implement, who cares if that's true if it just hemorrhages you a bunch of EV? I tell you what the simpler strategy is at all is just checking and then folding, right? But obviously that would just hemorrhage everything, right? You don't have to think about it, just check fold. You go to the next step, like, is this strategy more complicated than this strategy? Well, no, it doesn't really matter because the more complicated strategy can, and usually almost always does, yield a stronger in-game implementation of our own strategy. So improves our own strategy. So if we're learning from complicated, strong strategies, our own strategy will be stronger. We really need to think about how we're going to actually maximize the time that we study, right? If, say, for example, we have 100 hours or 1,000 hours, will we become a better poker player if we study the good strategy or the bad strategy? What is the answer? The answer should be pretty obvious, right? And it's the answer in other areas of life as well, that if you study how to do the better thing, right, the better strategy for a particular game or the better method of doing a particular thing, you'll end up being better at that particular game or method or technique or whatever, compared to studying, an outdated technique or an old strategy or inferior sort of ideas for the same amount of time. If we allocate that time to learning better techniques, better strategies, then we end up improving more for the same amount of time. The complicated strategies are larger, but we're not trying to memorize everything about them. We're just trying to gain as much information from them in our study time to improve our own strategy, our own implementation of how we play the game. Maximizing the use of our study time is going to be a topic for another video, but I'll just go over this briefly. The 4 key principles are: 1, the type of information studied should be sort of high quality and not random, right? So the information itself can't be random, right? You can't just study, rolling dice, because the order of the dice rolls is completely random. It doesn't really matter. The information that we should study should be high quality and not random. So if we create a high quality simulation, right, and we study it in a non-random way, we will get more out of it than studying poorer simulations in a random way. The next principle is that the new information should be absorbed through repetition. So we actually need to repeat the stuff that we've seen. We can't just look at the same thing once. We have to look at it multiple times. And looking at multiple times sort of embeds that particular idea into our mind much, much better than just looking at it once. Think about it for reading a book, right? If you read a book once, you're not really going to remember it. But if you have a favorite book and you've read it multiple times, you can remember passages off by heart. Or if you have a favorite movie or a favorite song, if you listen to it multiple times, watch it multiple times, you can repeat it just from memory, right? So it's repetition that embeds that information into our mind. The third principle is that the feedback loops should be quick or instant, meaning that if we get the answer wrong, we should be told almost immediately that our answer is wrong. In poker, you don't actually know whether an answer is correct or wrong because the outcomes are actually random. So studying poker by playing poker is just a horrible way of doing it, because the feedback is incorrect, the information is random, the spots are never repeated, and our feedback is just quite poor. And then finally, the fourth principle is that the difficulty of the training, so the stuff that we're actually learning, should be near the edge of our skill level, right? As close to the edge of our skill level as possible. So we're actually challenging ourselves to improve rather than just sort of repeating the same stuff over and over again. So, I mean, in poker, because the game is so large, this can be fairly easy. The new stuff that we learn, we might never have seen before, and there's plenty of stuff that we never have seen before. So it's important to learn new stuff, not just practice and repeat old stuff if we want to improve at poker. So that means that certain methods that people commonly use to study poker are actually really shit. So playing poker to improve is probably the worst way to actually get better at poker. If you look back at the 4 principles that we talked about, the information is random, the spots are never repeated, there's no feedback, and the difficulty of the training is just all over the place. So it's not near the edge of our skill. The spots could be, super easy or super hard, and we just don't know. So playing poker to learn poker is quite a bad way of actually doing things to improve. And similarly to that, playing against a GTO trainer is also going to be a poor method of studying poker, because all the spots will be random, you won't repeat them, and the difficulty of the training is probably also going to be mostly random. The spots could be really hard or really easy. You don't really know, because the spots are all given to you randomly. One thing that GTO trainers have over just playing poker is that the feedback is instant, right? You should be given the answer instantly if you make a mistake. Probably one of the best ways of studying is actually just hiring a coach. Having someone with, a lot of knowledge and experience is just a really good way to learn. So the coach gives you high quality information. The information is sort of tailored to your skill level. It's not random. If you have a coach and you've recorded the session, you can watch the session over again to get that repetition in. And the coach can give you pretty quick feedback. If you talk about a particular idea with the coach can essentially tell you almost immediately whether or not that idea is correct or wrong. So coaching is a really good way to, is a really good form of training, and you'll learn very, very quickly. Similar to coaching is paid training. So paid training has similar sorts of pros and cons. Many of the pros are still there in the fact that the information is usually quite high. Sorry, the type of information is usually quite high quality. The difficulty of the training can be tailored to your skill level. So you just buy the training that you think is appropriate for your level. You can repeat the videos while watching the videos more than once. The feedback can be given in the form of like quizzes to sort of test your knowledge, or you can discuss the training videos in the Zenith Poker Discord, for example. Although the feedback isn't quite as instant, and the training is not as tailored as it would be if you just bought a coach. All right, so that's all I had for today. Thank you for watching this video. Let me know what you think in the comments below. And yeah, remember, more bet sizes are better. Bye now.